What I thought I'd talk to you about today is mostly a software infrastructure project and a little bit of some applications for biophysical insight from that. But the hope is that this is some software that might be of interest and of use to some of you. The motivation for this is several-fold. That most molecular dynamic simulation packages are relatively monolithic, that there's some ability to do some plugins or custom code, but usually at a substantial performance cost. Most applications that people want to do are very frequently not. And at least from our end, looking at a lot of very innovative biophysical applications that happen to use MD codes that we help develop, we very frequently see people publishing with custom modified versions of the code. And we kind of think that is a bit of a waste of people's time, and it's a non-ideal situation. So one thing that we've been hoping to do is enable flexible yet performative use of large-scale MD simulations. We really believe strongly in having code that is out there and can be modified by the community, but having everyone have to modify it if they want to do something at all non-standard, we think is a bad idea. And so we'd like to be able to enable custom modifications without changes to the core MD code, and to have these run with performance approximating that of the native code. We've chosen to implement this strategy via a Python API to GROMACS. This is a little bit different both from some of the strategies that are out there that are essentially Python wrappers, and also from some of the very useful APIs to other MD codes, such as OpenMM, that are now available in Python. Our high-level design decision here is really inspired by TensorFlow, and the idea then, the key differences are twofold. One is rather than sequential procedural commands that then communicate directly and are executed by the MD engine, you have a set of commands that build a computational graph, and then that can be executed by a compute context. And so the idea that it's both not straightforward procedural, although hopefully transparent to people who are used to programming that way, and also rather than a direct Python execution, it's, if anyone's used TensorFlow, it's essentially you're talking to a back end. And I think if you think about this idea of a nice, happy Python environment and you're telling some back end what to do, that is also very, it was done for TensorFlow to try to optimize local GPU computation, but it's also very readily adaptable to HPC contexts, where you might be executing remotely, might be executing in parallel, and the form of the code doesn't really have to care about that too much. And this further, by setting a nice interface, enables performance optimizations to be done in a user-transparent manner. The final thing that motivated our particular design decisions was that we wanted, because a lot of what we do involves running not one simulation but many simulations, and we feel that's something that's increasingly common in the field, that ensembles should be first-class entities, and furthermore that the sort of computational backend should be somewhat abstracted, and to sort of separate the description of what to execute from the specification of where to execute. And this is work that's been inspired in part by some of our experience directly with GROMACS, our experience working on sort of advanced workflow software, and collaborations with others in the field, including Shantanu Jha. So therefore, we have designed and implemented the initial functionality for what we call GMX API, which is a high-level API for GROMACS, really targeted at Python, but also that has C++ API capabilities. And oops, okay, the key features are being able to initially to run MD simulations, of course, to have a clean interface rather than just to sort of take an MD code and expose all the library calls, to have a well-designed application programming interface to permit scalable and optimized execution with either standard MD code or custom user code, and then this computational graph abstraction. So what does this mean in practice, and what does this look like? This is an example of the high-level Python code to execute one particular task. And so it's essentially importing our GMX front end and then a custom written plugin, and setting up, in this case, a set of GROMACS work objects from a list of input files. So this could be one, this could be as many as you want. They could vary in any way you want. And then to connect that to a custom user plugin. And that's done in these three simple lines here. And then to initiate a parallel execution context connected to this MD object, and then in syntax that would be familiar to anyone who's used TensorFlow to run this. And so the top level Python code is simple, clean, and executes an arbitrary ensemble of simulations using a custom potential. So that's the kind of outline that we currently have implemented and running. This is in alpha beta. And really what this ends up, oh, okay, apparently I'm supposed to go this way. So really what this ends up looking like under the hood is that this initialization then sets up the first stages of a computational graph, data input, and MD engine instance with a dependency on this data, setting up the potential, then adds elements to the computational graph, both a plugin module that has connections to the MD engine, and then optionally, as I'll talk about in our plugin model, in this case, we are running an ensemble, doing an ensemble reduce and a set of calculations across the ensemble, and using that to update the plugin. And then finally, the execution passes this graph to an execution manager. So that's the outline of how this works. Custom potentials are designed to be very easy to implement. Right now, I would say they are much easier than writing your own custom code. There's a little bit more modification of boilerplate code than we'd ideally like, but this is still relatively straightforward, as people who are in the room who have tried this can attest. And the goal is, by the time of the next stage of releases, to have very straightforward templated code, because there are really two things that need to be implemented. One is a method to calculate a potential given the appropriate data that is sort of simulation current on positions and time, and then a callback if there's any adaptive update functionality in the custom potential, and that adaptive update can again be individual simulation specific, or it can have a dependency across the simulations. And so what we've initially used this for is to re-implement a restrained ensemble simulation formalism that Benoit Roux has designed and published. This is primarily was intended for incorporating data from EPR, from deer spectroscopy into simulations. And what this does, we have a slight modification of Benoit's method, but it's essentially Benoit's code, Benoit's algorithm that we've implemented in our own code, is to run an ensemble of simulations to compute an observable, the distribution of the observable across the ensemble at regular intervals, and to compare the estimated distribution to the experimental observed distribution, and to derive a biasing potential from the difference between the estimated and the target distributions. When we implement this using GMX API, our performance is within 5% of a native code implementation that we did modifying GROMACS. Both of these run nicely in parallel. The GROMACS API, in this case, we're running a number of ensemble members and having a blocking reduce across the ensemble members and then continuing. If there's no need for a reduce, each ensemble member can run, update, keep running in a completely independent fashion. So it depends on the needs of the application, and all of this is, again, transparently specified in the computational graph. And so there's no specific saying, okay, this is blocking, this is not blocking. If there's a data dependency on a reduce, then the execution manager implements that. So we've done this in a manuscript for a flexible bacterial outer membrane protein, where we ran an ensemble of 20 simulations, performing an ensemble reduce and potential update every 100 picoseconds. Run this for, depending on the needs, 100 or 200 nanoseconds, and get relatively rapid convergence, in this particular case, to the experimental distributions. I'm showing on the top in light gray were the initial starting distributions at the beginning of this restrained ensemble simulation. In black are the distributions from deer spectroscopy, and then in heavy color is the estimated distribution from the simulation ensemble after 100 nanoseconds. And then if you look at the Jensen-Shannon divergence, some of these sort of pair restraint observables converge extremely quickly, and some take a little bit longer to converge in this particular set of simulations. But Jensen-Shannon divergence is a good way to estimate agreement of distributions, and we use that to monitor convergence over time. So the current status of this code is the pieces of functionality that we have enabled in a pre-release version are running ensembles, custom force plugins, the ensemble reduce as needed. We've implemented this for 2 different ensemble biasing algorithms. The next thing we'll be doing is an automated pulling runs and umbrella samplings to calculate PMFs. We do have an alpha beta code release. This is probably within about a day or 2 of running on blue waters. We're very close. The Python environments are a little more challenging, as most of you know. What we're doing right now is expanding the functionality of the code. Obviously, one of the key things that you'd like to be able to do is load a set of run input files and vary one or a few parameters systematically across an ensemble of simulations. And that's the next thing that should be out very shortly. But we're also taking requests. If there are pieces of functionality that would be absolutely key to your using this, please let us know and we'll try to prioritize those. So we would like to hear from you about this. The initial manuscript describing GMX API at a high level is on bioRxiv. Also, the first, the Restraint Ensemble application, the bioRxiv paper is actually using the native modified GROMACS code, but all this is fully implemented also in GMX API. You can get the software from GitHub, and we're always looking for more people to join our team. So let me know if you're interested in that. The people who did this work, Eric Eargang is a talented postdoc software developer in the group who's implemented GMX API. Jennifer Hayes, who's here, has been working on the scientific applications and also saying when the code doesn't work and when it doesn't actually perform to user specs, which is key feedback for someone trying to write this. The other members of my group are here, and this is, in a number of ways, touches on collaborative work with members of the GROMACS team, especially Eric Lindahl, Mark Abraham, Michael Schertz, and Linda Columbus and her group on the spectroscopy, and Shantanu Jha. And I should also call out a lot of really useful and helpful interactions with Tom Cheatham. So thank you. We're thankful also to NSF and NIH for funding, and thank you for your time.